In this video, we're going to look at residual plots a little bit more. So in the past, we have looked at a couple of things to tell whether or not a set of data could be modeled by a linear regression line. And the first thing we did was we looked at a scatter plot and we said, do we think this looks linear in form versus does it look curved? So that was our first thing we could check, was we looked at the scatter plot to see how it looked. The second thing we did was we looked at the R value, and we knew that the closer that R was to either +1 or -1, that was also a good sign that our data might be linear. So now we're looking for some more tools. So the next tool we can use is to look at the residual plot. So the graph on the left is just your plain old scatter plot. It's got your explanatory variable on the x-axis and your response variable on the y-axis. The scatter plot on the right is your residual plot. It still has the explanatory variable on the x-axis, but then the y-axis is the residuals. So remember, the residual was how far away each of these points over here, so this distance here is your residual. It's taking each of those points and then putting them over here and saying how far away was that residual, or that point, how far away was it from the actual value. So that's what's being plotted here on the y-axis. And this residual plot is actually a very good one. What you want to see in a residual plot is a random scatter with no pattern. If you see a residual plot that has a pattern, then that is a hint that your data was not linear. So here, the graph on your right is the original scatter plot, and you can see a curve there, but maybe this curve would be more subtle and you couldn't see it. That would become apparent on the residual plot, the graph on the left. That's much more obvious that you can see a pattern. So that's one kind of pattern you might see. Another pattern you might see on your residual plot is something that we call a fan pattern, or a sideways Christmas tree pattern. So if it looks like the residuals are pretty small on one end and larger on the other end, then that's also a pattern. So we're looking for things like parabolas or exponentials to show up in the residual plot or this fan pattern. And again, those would be things that would go against thinking that our original scatter plot was linear. So we like to have a random scatter in the residuals. Now there will be a video for you to use your calculator. You'll have to put your original data in list 1 and list 2 in your calculator, and then you'll run the regression and store the residuals in list 3, and then there will be a way to make the scatter plot on your calculator of the residuals. So make sure you take a look at that before you move on to the practice problems. So just like we can find standard deviation of any list of numbers, we can also find the standard deviation of the list of the residuals. There's a formula for that. Again, you're not really going to be required to know that because your calculator will do this for you. One thing to notice is you'll remember that when we did the standard deviation formula for just a plain old list of numbers, we divided by n if that list of numbers was a population. We divided by n minus 1 if that number was a sample, and we did that because we wanted to acknowledge that there was a little bit more error in a sample than in a population. And here, when we're looking at a least squared regression line and then the residuals, we divide by n minus 2. Again, that's because there's just even more error when you've got two lists of numbers that you're trying to work with. Again, your calculator will do this for you, so don't worry too much about this formula. But you should know that a residual, when you find the standard deviation, you would interpret it in much the same way as you would the standard deviation of just a list of numbers. So this is where you say something like the actual price of the truck is typically about $1,200 away from the predicted cost according to the least squared regression line, something like that. You have that same how far away is it from the mean kind of fill in the blank sentence when you go to interpret that. Now there's also something else called the coefficient of determination. That's just r squared. So you already know how to put your data in your calculator and get the value for r. You just square that number, so multiply it by itself. And that gives you r squared, which we're calling the coefficient of determination. The coefficient of determination tells you how much of the variability in whatever your y context is accounted for by your least squared regression line. So we want this value to be as close to 100% as possible. So this is another thing that we can look for. So far we've got a scatter plot, we look for it to be close to linear. We've got the r value, we want it to be as close to +1 or -1 as possible. We've got the residual plot, we want it to be a random scatter. We've got the standard deviation, which ideally we'd want that to be as close to 0 as possible. And then here we've got the r squared, and we'd want that to be as close to 100% as possible. So let's put this all together and look at an example. So here we have, on the left is our scatter plot with our points per game as the explanatory variable and the number of games won as the response variable. We've got our least squared regression line, so our y hat equation. And then on the right, we've got our residual plot, and we see that it's got a random scatter, so that's all good. And again, your calculator will be giving you the values for the standard deviation of the residual and the coefficient of determination, your r squared. So what we want to do is we want to look at all of these things and use this model and answer some questions related to the model. So recall that equation that we came up with was using the x as the points per game and then the y value as the expected number of wins that they would have. So here they're asking us to calculate the residual for a team that scores 30.1 points per game and has 11 wins. So first we plug in the points per game for x and solve for y. So the predicted number of wins would be the 9.4. And then remember, the residual is the actual value minus the predicted value. So our residual is 1.6. So the way we would interpret this is that this team won 1.6 games more than what we predicted it to. Now we also have this data about the standard deviation and the coefficient of determination and what those mean. So remember, we're looking at all of these things. We saw the scatter plot, and then we looked at the residual, and we didn't see an obvious pattern. We want our S value to be as close to 0 as possible. We want our R squared to be as close to 100% as possible. And now in the interpretation. So remember, standard deviation tells you typically how far off any of your answers might be from the average. So here we expect any team, if we take their points per game, we expect to be off by about 1.2 wins from what we predict to the actual. And then the R squared value, remember, that tells you the percentage of the variability, in this case of the number of wins, that's accounted for by your least squared regression line. So 88% of the variation of wins is accounted by our least squared regression line for the model of points per game versus wins. All right, and last thing is to know that a lot of times you're not even going to need to enter the data into your calculator to answer questions. You're going to be given computer output. So I'm going to show you two examples of that. This one here is the type of output you would see from something called Minitab. And the way I like to look at this is I know that the coefficient column is going to give me my slope and my y-intercept. Know that constant, in terms of like your y hat equals a plus bx. So your constant is that a value. Your constant doesn't have the x next to it versus the coefficient is your miles driven. So I remember whichever one says constant, that's the one that is my y-intercept. That helps me with that. Your s is over here. That's your standard deviation of the residuals. Remember, your slope is your other coefficient. And then doesn't give you the R value, but it does give you the R squared value. So it gives you that coefficient of determination. If you need to work backwards and get your correlation coefficient or your R, remember if you need to start with, you have an R squared value and you need to get your R, you're going to do that by taking the square root. Now the trick here is that this value could be positive or negative, and you have to figure out which one of those it is. You tell that from your slope. So if your slope was positive, then your R value will be positive. If your slope was negative, then your R value will be negative. So even though this computer output doesn't give you the R value directly, you can get it from the R squared value. Now these other things here we're going to talk about at some other time. We'll come back to those later. Here's another example of some computer output that you would get, and you should look for some similar things. This time, instead of constant, they've got a column called estimate, and then instead of the constant over here, they've got just the intercept, so it's a little easier to tell which one's the y-intercept and which one's the slope. So the one that has like your units of your explanatory variable, that's the one, that's how you're going to know that that's your slope. And then the R squared, that's labeled. What's a little trickier here, your standard deviation of residuals, they're calling the root mean squared error. So the first one, the mini tab, is going to be a little bit more common, but this is just a variation of what you might see. And again, we'll talk about all these other things at a later time. We'll come back to them later. All right, don't forget to go through the video on your residuals before you try the practice problems, and then eventually move on to your next section.